Good day, class. Today, we are in the transition from site planning to the building itself. On our previous module, we studied the following: climate, environmental analysis, passive environmental systems, site planning, and microclimate modifications. Now, we examine the physical components that separates people from climate. These components collectively form the building envelope. The building envelope acts as the protective skin of architecture. Every day, it is exposed to the following: solar radiation, wind, rain, humidity, moisture, and temperature fluctuations. The performance of the building envelope largely determines comfort, energy consumption, durability, sustainability. In tropical climates, building envelopes faces unique environmental challenges. So architects must therefore understand how roofs, walls, materials, and construction systems responds to these conditions. This topic forms one of the most important foundations of climate responsive architecture. The objectives of this module focuses on understanding environmental performances at the building component level. As architects, we must move beyond aesthetics. A beautiful building that performs poorly environmentally is ultimately unsuccessful. By the end of this topic, you should understand how tropical climate affects building performance, how heat enters buildings, how moisture affects materials, how building systems can improve occupant comfort, how materials influences sustainability. And these competencies are essential for both professional practice and licensure preparation. The building envelope can be understood as the interface between people and climate. Everything outside the building envelope belongs to the external environment. Everything inside the envelope belongs to the internal environment. The envelope regulates heat, light, air, moisture, and sound. Its performance determines how effectively a building protects occupants from environmental extremes. When architects make decisions about roofs, walls, windows, and materials, they are making environmental decisions. Therefore, understanding the building envelope is fundamental to climate responsive design. Before designing buildings, architects must understand the climate they are responding to. Hot, humid, tropical climates are characterized by high temperatures, high humidity, frequent rainfall, and strong solar exposure. Unlike temperate climates, the primary challenge is usually not retaining heat. Instead, the challenge is controlling heat gain and managing moisture. These environmental conditions creates unique design requirements. Buildings that performs well in cold climates may perform poorly in tropical climates. Therefore, climate-specific design is essential. Hot, humid climates presents several environmental challenges. The first challenge is heat. Excessive heat gain creates discomfort and increases cooling demand. The second challenge is humidity. High humidity reduces the effectiveness of natural cooling mechanisms within the human body. The third challenge is moisture. Moisture affects both occupants and buildings. It can lead to mold, mildew, material degradation, and poor indoor air quality. Architects must therefore address both thermal and moisture performance simultaneously. Ignoring either issue often leads to long-term building failures. Thermal comfort is ultimately the reason we study building envelopes. People occupy buildings to achieve comfort. Comfort is influenced by multiple environmental variables: temperature, humidity, air movement, radiant heat, and surface temperatures. A successful tropical building envelope moderates these environmental conditions and creates spaces that supports human well-being. Good envelope design therefore directly contributes to the quality of life. Understanding heat transfer is essential for architects. Heat enters buildings through three primary mechanisms: conduction, convection, radiation. Most tropical heat gain originates from solar radiation. This heat is then transferred through building materials and eventually enters occupied spaces. The building envelope functions as a control system that manages these heat flows. The better architects understand heat transfer, the better they can design high-performance buildings. The building envelope acts as an environmental filter. Its role is not to completely block environmental forces. Instead, it selectively manages them. For example, we want daylight, but not excessive heat. We want ventilation, but not water intrusion. We want outer connection, but also protection. The building envelope, therefore, becomes a carefully calibrated environmental control system. Before discussing roof types, we must first understand why roofs occupy such a significant role in tropical architecture. Among all components of the building envelope, roofs are often the most environmentally important. Why? Because roofs receives the greatest environmental exposure. Consider the environmental forces acting upon a roof every day. First, solar radiation. In tropical climates, the sun is intense and often positioned at relatively high angles throughout the year. This means roofs receives direct solar exposure for extended periods. Unlike walls, which may be shaded part of the day, roofs often remain exposed continuously. Second, rainfall. Tropical climates frequently experience intense rainfall events. A roof must not only prevent water intrusion, but also manage drainage efficiently. Third, wind. Strong tropical storms, typhoons, and monsoons place significant demands on roof systems. Fourth, heat transfer. The roof becomes one of the primary pathways through which heat enters buildings. Studies consistently shows that a substantial percentage of indoor heat gain originates from the roof. Therefore, when architects design tropical buildings, roof design is never simply a matter of aesthetics. Roof design becomes an environmental decision. The roof affects thermal comfort, energy consumption, ventilation performance, durability, and occupant well-being. Traditional tropical architecture recognized this principle centuries ago. Large roof forms, steep slopes, extended eaves, and ventilated attic spaces were not merely stylistic choices. They were environmental responses. As we move through this section, I want you to think of the roof not simply as a covering. Think of it as the building's first environmental defense system. Many people assume that a roof performs only one function, keeping rain out. While this is certainly important, tropical roof systems performs far more complex roles. A successful tropical roof simultaneously manages heat, moisture, air movement, environmental comfort. So let us examine each function. Heat management is perhaps the most critical. Without proper design, solar radiation heats roof surfaces dramatically. This heat eventually transfers indoors. Consequently, indoor temperature rise and cooling demands increase. The second function is moisture protection. Tropical rainfall can be intense. Roofs must quickly shed water while preventing leakage and material deterioration. The third function is ventilation. Many traditional tropical roof systems intentionally incorporated ventilation spaces. These systems allowed heat to escape before it entered occupied spaces. This simple strategy significantly improved thermal comfort. Modern architects often focus heavily on appearance while neglecting environmental performance. However, the best tropical roofs combine aesthetics and environmental intelligence. Throughout history, tropical architecture evolved several highly effective roof design principles. The first is large roof overhangs. Overhangs protects walls from both sunlight and rain. The seemingly simple features dramatically improves building performance. The second is steep roof slopes. Heavy rainfall requires efficient water shedding. Steeper roofs reduces water accumulation and improve drainage. The third is roof ventilation. Ventilated attic spaces allows heat to escape before reaching occupied rooms. This reduces indoor temperatures significantly. The fourth principle is lightweight construction. Heavy rainfall or heavy materials stores heat. Lightweight materials responds more quickly to changing environmental conditions. Traditional tropical architecture applied these principles remarkably well. Modern architecture often benefits from revisiting these lessons. Traditional tropical architecture provides some of the best examples of climate-responsive roof design. Long before mechanical cooling existed, communities successfully created comfortable environments through intelligent roof design. The Bahay Kubo illustrates this beautifully. Its steep roof sheds rain rapidly. Its large overhangs provide extensive shading. Its ventilated construction promotes airflow. Similarly, traditional Malay houses incorporated elevated floors and highly ventilated roof systems. Balinese architecture developed large roof volumes that facilitated heat dissipation. These examples demonstrates an important lesson. Traditional architecture often evolved through centuries of environmental adaptation. As architects, we should study these systems not because they are old, but because many remain environmentally effective until today. As architecture evolved, new technologies became available. However, the environmental challenges of tropical climates remained largely unchanged. Architects still faces heat, humidity, rainfall, and solar exposure. Modern tropical roof systems therefore build upon traditional principles while incorporating contemporary materials and technologies. One example is the double roof system. In a double roof configuration, two roof layers are separated by an air cavity. This cavity acts as a thermal buffer. Heat absorbed by the outdoor roof dissipates before reaching the interior. Another example is ventilated roof cavities. By allowing air to circulate beneath roofing materials, heat buildup is reduced. Reflective roofing systems are also increasingly common. These materials reflect solar radiation rather than absorbing it. The result is lower roof temperatures and reduced cooling demand. Modern technology should not replace environmental wisdom. Instead, it should enhance it. One of the most effective roof technologies available today is the cool roof. A cool roof is specifically designed to minimize solar heat absorption. Traditional dark roof absorbs large amounts of solar energy. This energy is converted into heat. Consequently, roof temperatures rise dramatically. Cool roofs functions differently. Their surfaces reflect a larger percentage of incoming solar radiation. As a result, roof temperatures decrease. Indoor temperatures decrease. Cooling requirements decrease. The impact can be significant. Studies consistently shows measurable reductions in building energy consumption when cool roof technologies are implemented properly. For tropical regions where solar exposure is intense year-round, cool roofs offers a practical and highly effective environmental strategy. Green roofs represent a fascinating intersection between architecture and ecology. Unlike conventional roofs, green roofs incorporate living vegetation directly into the building envelope. These systems provide multiple environmental benefits simultaneously. First, vegetation shades roof surfaces. Second, evapotranspiration cools surrounding air. Third, green roofs reduce storm water runoff. Fourth, they contribute to biodiversity with urban environments. However, green roofs are not appropriate for every project. Architects must consider structural capacity, maintenance requirements, water management, and plant selection. When designed properly, green roofs can significantly improve environmental performance while creating visually compelling architecture. After roofs, walls become the next critical building envelope component. Walls do far more than simply separate interior and exterior spaces. They regulate environmental exchange. Every wall interacts continuously with heat, moisture, air, and light. In tropical climates, walls must balance competing objectives. We want protection from solar heat gain. We want moisture resistance. We want airflow. And we want daylight. These requirements often conflict with one another. The architect's task is to find the optimal balance. Wall design therefore becomes an environmental design exercise rather than merely a structural or aesthetic decision. Wall systems can generally be categorized as lightweight, heavyweight, or hybrid. Lightweight systems respond quickly to environmental changes. Examples include bamboo, timber, and engineered wood products. These materials typically store less heat. Heavyweight systems include concrete, masonry, and stone. This material possess higher thermal mass. Thermal mass can be beneficial or problematic depending on climate conditions and design strategies. Hybrid systems combine the strengths of multiple materials. Modern tropical architecture increasingly utilizes hybrid assemblies because they provide greater environmental flexibility. Understanding the strengths and limitations of each wall system allows architects to make informed decisions. Thermal mass is one of the most misunderstood concepts in architecture. Many people assume that high thermal mass is always beneficial. This is not necessarily true. The effectiveness of thermal mass depends on climate. In hot, arid climates, thermal mass can be moderate temperature fluctuations. In hot, humid tropical climates, excessive thermal mass may create problems if heat cannot dissipate effectively. Materials such as concrete absorbs heat during the day. If nighttime, cooling is limited. Stored heat may continue affecting occupants after sunset. Therefore, architects must understand not only the material itself, but also the environmental context in which it operates. Architecture students associate insulation exclusively with cold climates. This is a common misconception. Insulation functions by slowing heat transfer. In tropical climates, insulation helps prevent external heat from entering interior spaces. The greatest benefits often occur in roof assemblies because roofs receives the highest solar exposure. Effective insulation reduces indoor temperatures, cooling demand, and energy consumption. However, insulation must be combined with ventilation and moisture management. Otherwise, unintended environmental problems may occur. Ventilated wall systems create an air gap between exterior and interior wall layers. The airspace functions as a thermal buffer. Solar heat absorbed by the outer layer is dissipated before reaching occupied spaces. Ventilated facades are increasingly common in contemporary tropical architecture because they improve both thermal and moisture performance. This system illustrates an important principle. Sometimes, the most effective environmental strategy is not adding more material. Sometimes, it is creating space for air movement. Many architects focuses heavily on temperature and energy consumption. However, in tropical climates, moisture is often the greater long-term threat. Moisture affects nearly every component of a building. It affects structural systems, finishes, mechanical systems, occupant health, and indoor air quality. One reason moisture is so problematic is because its effects are often invisible during the early stages. A building may appear perfectly functional, while hidden moisture accumulates within walls, ceilings, and floor systems. Over time, this hidden moisture creates serious problems. Mold develops, materials deteriorate, indoor environments become unhealthy, repair costs increase dramatically. Tropical climates create particularly challenging moisture conditions because humidity remains elevated throughout much of the year. This means architects must think about moisture constantly. Every design decision should consider how does water enter, how does water live, how does the building dry, and buildings that cannot dry eventually fail. Understanding moisture is therefore one of the most important responsibilities of tropical architects. To control moisture, we must first understand where it comes from. Most architects immediately think about rain. While rain is important, it is only one source of moisture. Moisture enters buildings from multiple directions. Externally, moisture originates from rainfall, groundwater, flood waters, humid outdoor air. Internally, moisture originates from human respiration, cooking activities, showers, laundry, mechanical equipment, and plumbing failures. A single family can generate several liters of water vapor every day simply through normal living activities. This moisture accumulates continuously. If buildings are not designed to manage it effectively, humidity levels increase and problems emerge. Therefore, moisture management must address both external and internal sources simultaneously. A good building envelopes functions as moisture management systems. One of the most misunderstood building science concepts is condensation. Condensation occurs when water vapor transforms into liquid water. This process happens whenever warm, humid air contacts a cooler surface. In tropical climates, Condensation frequently occurs inside walls, inside roofs, behind ceilings, around windows, within air-conditioned spaces. The danger is that condensation often remains hidden. Occupants may not notice problems until significant damages has already occurred. Moisture accumulation creates ideal conditions for mold growth. Mold not only damages materials, but also affects human health. Architects must therefore understand dew point behavior, humidity movement, and temperature differentials. Failure to address condensation can compromise the entire building envelope. A beautiful building that cannot manage condensation will eventually experience performance failures. Moisture control requires a comprehensive strategy. The first objective is preventing water entry. Architects accomplish this through roof systems, drainage design, waterproofing systems, and flashing details. The second objective is promoting drying. Even well-designed buildings occasionally experience moisture intrusion. Therefore, buildings must possess the ability to dry. Traditional tropical architecture often excelled in this regard. Highly ventilated assemblies allowed moisture to dissipate naturally. Modern sealed buildings sometimes struggle because trapped moisture has nowhere to escape. The third objective is humidity management. Ventilation systems, airflow pathways, and environmental controls all contribute to maintaining a healthy indoor conditions. The most successful tropical buildings are not necessarily those that keep all water out. They are the buildings that manage moisture intelligently. Material selection influences far more than appearance. Every material carries environmental consequences. Sustainable tropical materials generally possess several desirable characteristics. They are renewable, durable, locally available, and environmentally responsible. Local materials often provide additional benefits. Transportation impacts are reduced. Regional construction knowledge is preserved. Economic benefits remain within local communities. Bamboo is one excellent example. Its rapid growth rate makes it highly renewable. Engineered timber systems are another important development. These technologies allows architects to create sophisticated structures while reducing embodied carbon. Material selection should therefore be viewed as an environmental decision rather than simply a design preference. Vernacular architecture represents centuries of environmental experimentation. These buildings evolved gradually through observations and adaptation. They responded directly to climate conditions. Unlike many contemporary buildings, vernacular structures often achieved remarkable environmental performance without advanced technologies. Common characteristics include large roof overhangs, natural ventilation, lightweight materials, elevated construction, and climate-responsive forms. Studying vernacular architecture provides a valuable lessons for a modern practice. The objective is not to copy traditional buildings exactly. Rather, the goal is to understand the environmental principles underlying their success. At this point on our lecture, we have discussed roofs, walls, insulation, moisture control, and sustainable materials. However, architects must understand a more fundamental question. Why do some materials perform better than others in tropical climates? The answer lies in thermal performance. Thermal performance refers to how materials respond when exposed to heat. Every material interacts differently with solar radiation. Every material stores, transfers, and releases heat differently. Understanding these differences is one of the most important competencies in climate responsive architecture. Let us examine several critical thermal properties. The first is thermal conductivity. Thermal conductivity measures how quickly heat moves through a material. Materials with high conductivity transfers heat rapidly. Materials with low conductivity transfers heat more slowly. For example, metals generally conduct heat quickly. Insulation materials conduct heat slowly. The second property is thermal mass. Thermal mass refers to a material's ability to absorb and store heat energy. Materials such as concrete and stone possess high thermal mass. Materials such as bamboo and lightweight timber possess lower thermal mass. The third property is solar reflectance. Reflective materials absorbs less solar energy. Consequently, they remain cooler under direct sunlight. The fourth property is thermal resistance. This measures how effectively a building assembly resists heat transfer. Understanding these concepts allows architects to evaluate materials scientifically rather than emotionally. Material selection should never be based solely on appearance. The most beautiful material may perform poorly in tropical conditions, and the most successful architects, designers, understands both aesthetic and environmental performance. One of the most common misunderstandings among architecture is the belief that modern materials are automatically superior to traditional materials. This assumption deserves critical examination. Traditional materials evolved through centuries of environmental adaptation. Communities selected materials based on climate, availability, performance, and constructability. Bamboo, for example, remains one of the most environmentally responsive materials available. Its lightweight nature reduces heat storage. Its renewability makes it environmentally sustainable. Its flexibility provides structural advantages. However, traditional materials may also present challenges like durability concerns, maintenance requirements, code compliance issues. Contemporary materials offers different advantages. Engineered timber products provide improved structural performance. Advanced insulation systems improve thermal comfort. Composite wall systems offer enhanced durability. The key lesson is this: the objective is not choosing traditional over modern. The objective is selecting the most appropriate material for a specific environmental context. Good architecture avoids ideological thinking. Good architecture relies on evidence-based decision-making. The future of tropical architecture will likely involve hybrid solutions that combine traditional environmental wisdom with modern technological capabilities. As architects, your responsibility is not to blindly follow trends. Your responsibility is to evaluate performance. As we conclude this module, it is important to recognize that tropical architecture is ultimately about environmental response. Every building envelope decision influences environmental performance. Every roof, every wall, every material, and every connection detail. Throughout this topic, we explored how tropical climates create unique challenges. These challenges includes heat, humidity, moisture, rainfall, and solar radiation. Architects must address all of these conditions simultaneously. Successful tropical building envelopes do not depend on a single strategy. Instead, they combine multiple environmental responses. A successful tropical building might include a reflective roof, ventilated roof cavities, proper insulation, moisture-resistant assemblies, climate-responsive materials, and natural ventilation systems. When these systems work together, environmental performance improves dramatically. The most important lesson is that architecture is never separate from climate. Climate influences every design decision. As future architects, you must learn to see buildings not merely as objects. You must see them as environmental systems. The mindset forms the foundation of sustainable and climate-responsive practice. It is also the mindset expected of professional architects and licensure candidates. As we conclude our discussion on tropical building envelope and materials, we must now begin asking a much larger question. Up to this point, we have focused primarily on how buildings respond to environmental conditions. We studied climate analysis, site planning, microclimates, passive environmental systems, building envelopes, and material performance. These topics helps us understand how to create environmentally responsive buildings. However, contemporary architecture faces a challenge far greater than environmental comfort alone. That challenge is resilience. Today, architects are designing within a rapidly changing world. We are experiencing rising temperatures, more intense storms, increased flooding, sea level rise, resource scarcity, and growing urban populations. As a result, architecture can no longer focus solely on functionality and aesthetics. Architecture must also address uncertainty. This brings us to our next major topic: tropical sustainability and resilience. The word sustainability is often misunderstood. Many people associate sustainability only with environmental protection. In reality, sustainability refers to the ability of systems to endure over time. Similarly, resilience refers to the ability of systems to adapt, recover, and continue functioning despite disruptions. On our next module, we will explore how architecture responds to these challenges. First, we will examine climate resilience. How should architects design buildings capable of performing under changing climatic conditions? Second, we will investigate disaster responsive architecture. Tropical regions are among the most hazard prone environments in the world. Architects must understand how design decisions influence vulnerability and resilience. Third, we will study typhoon resistant design strategies. In countries such as the Philippines, typhoons represents one of the most significant environmental threats. Understanding wind forces, structural resilience, and envelope protection is therefore essential. Fourth, we will explore net zero tropical design. As energy consumption continues to increase globally, architects are being challenged to create buildings that generate as much energy as they consume. This represents one of the most important sustainability goals of the 21st century. Fifth, we will discuss carbon-conscious architecture. Buildings contribute significantly to global carbon emissions. Architects therefore play a critical role in reducing environmental impacts through design and material selection. Finally, we will examine sustainable tropical communities. Architecture does not exist in isolation. Individual buildings are part of a larger environmental, social, and economic systems. The ultimate goal is not simply sustainable buildings. The ultimate goal is sustainable communities. By the end of the topic 6, we will understand how architects can contribute to climate adaptation, disaster resilience, carbon reduction, sustainable development, and community resilience. These topics are becoming increasingly important within professional practice, international sustainability frameworks, and future architectural licensure exams. The future architect is no longer simply a building designer. The future architect is a climate responsive problem solver, a resilience strategist, and a steward of sustainable development. This concludes our topic today, tropical building envelopes and materials. On our next lecture, we begin exploring the future of tropical architecture through sustainability and resilience.